Good morning, everyone. Hope you're all doing well on another kind of cruddy, rainy day, but I guess we need these cruddy, rainy days to make the area we live in so beautiful and lush and green. So good day to stay in and snuggle with your dog and study for your Chem 130 exam, which your Chem 130 final, which is coming up on Sunday, Monday. So don't miss out on that. You've got one more lab left. It is sort of a similar structure setup to the last one in that it is available for you online and you'll just fill it out and then resubmit it. And it's very, once again, kind of definition based. So let's go to the lab section here. You'll see it's right here, the amino acids lab, and you'll submit it on Sunday as well. You may want to do it earlier. So like, hold on one second. Now I'm questioning myself on my dates. I'm getting all of my class sections mixed up. Let's look at the just to be sure. Thought you only had one test left, but I guess you actually have you do have one test and you have your final. Okay, I like that. Bio. Okay, yeah, so I just want to double check that that's what's on the syllabus as well. I think I was mixing you all up with my 092 class. Okay, so you have a final test, which will be Sunday, Monday. And then you have a final exam. The final exam will be open Monday through Tuesday. Yes, that's what it is. Okay. So the final exam needs to get wrapped up by 5/11. Now I remember, yeah, because unfortunately I have to turn around and put the grades in by 5/12. So I try to give you as much time as possible, but I didn't want these to be exactly on the same day. So just note that it's going to be test, or test final. So if we look over here, and I want to be clear about the hours, we have it available. Yeah, so test 5 will be Sunday at 5 a.m. till Monday at 11:59 p.m. And then the final exam will be Monday at 5 a.m. and Tuesday until, it looks like it's only open until 5 p.m. So please make note of that. It's only open until 5 p.m. Again, the reason it's only open until 5 p.m. is because I have to go around and turn your grades in like the next morning at like 8 a.m. So make sure you are allotting time. I would recommend getting this test 5 done on Sunday as soon as you can. And then, when that final exam opens, the sooner you can take it, at least from my end, the better. But if you're not taking it until 5, that'll work. Okay, so let's get through amino acids. One second, my door's There is an additional chapter that you will see on Moodle for nucleic acids. It said we'd get to if time allotted. We aren't going to do that. Not necessary. It's not covered on the final. And, you know, we're in the last rung here of a pandemic. So we're just going to make it as simple as possible. So no need to do that last chapter. But this chapter we will want. Okay, so chapter 16, amino acids, proteins, and enzymes. Again, this is going to be a lot of definition-based stuff. So the last chapter, or, you know, if you get it conceptually, that's great. If not, you know, just memorize it. So protein molecules, compared with many of the other compounds we have studied in this class, are absolutely gigantic. Okay, a lot of what we dealt with in the first part of this class was inorganic stuff, which is like a lot of times just 2, maybe 3 things mixed together. Then we went into organics. Organics, you know, you can have some clunky molecules. When we got into carbohydrates, they got a little bit bigger. Proteins and amino acids are huge. If we look at this animal over here, the horns of this guy are all made up of proteins, and actually not just the horns, his fur and his eyes and pretty much everything on his body is made up of some type of amino acid, which is just a chain of, or I'm sorry, some type of protein, which is just a chain of amino acids. So when we're talking about a protein, when somebody says, oh, you know, I need protein, or, you know, your body is made out of protein, your hair has got protein, collagen, a type of protein, all these things. What is a protein? Proteins in the body are polymers meaning multiple amino acids made from, and they're made up of 20 different types of amino acids. So there's not an infinite amount of amino acids that we find in our body. There are roughly 20 of them. If you're in like a true biochem class, like dedicated just to biochem, you would probably have to have all 20 of those amino acids memorized. Just because of the nature of this class, we're just kind of touching on things because there's so much information. You do not need to have the amino acids memorized. You do need to have the root of the amino acid, which is the same in each amino acid memorized. And I'll show you that in a little bit. They differ in characteristics and functions that depend on the ordering of the amino acids that make up the protein. So we've got this protein, it's made up of amino acids. Depending on what type of amino acids you have within your chain and how many of them you have and what order they're in, you'll get a bunch of different things. We've got structural components of the body. So cartilage, muscle, hair, and nails are all made up of specific types of proteins. We also have functional enzymes, which help regulate our biological reactions. This is for digestion, cellular metabolism. Those are all also types of proteins. Those enzymes are proteins. Things like hemoglobin and myoglobin, which transport oxygen in the blood, those are also examples of proteins. And so we sort of categorize bodily proteins by how they function. So there's, you know, structural, contractile. This is for making muscles move. If it's transporting things, is its job to deliver nutrition or other things to certain parts of the body. Storage, so things like storing fat, storing protein in milk, hormones, all those are proteins. Enzymes, proteins, things for protection are also types of proteins. So like our immune response, when it recognizes a foreign body and it will destroy it. So we're all just a bunch of protein. That's why if, you know, you happen to be vegetarian or vegan, you do need to be consuming protein from some other source. It does not do you any good to only eat pasta, right? With nothing on it. You'd need to have some cheese or some nut cheese or something that would give you protein. So here is an amino acid. This is a really simple amino acid. And there is part of it that you do have to have memorized and or understand. So the amino acid is our molecular building block for a protein. It will have a central atom or a central carbon atom, which is called the alpha carbon. So that's this thing right here. So when looking at this structure, this right here, this sort of tail end, this is always the same. For every single amino acid, you will have this component. This R group, or this guy right here, changes. And that's what makes it one amino acid versus another amino acid, okay? So we will always have this lump of stuff here. This will switch out. This is a very simple one. It's just a methyl group at the end. So let's talk about what's in the similar tail end of an amino acid. We have our alpha carbon, and then attached to the alpha carbon will be a hydrogen. Okay, so this carbon, remember, carbon always likes 4 buddies. So one of its buddies is this R group that changes out. The other 3 buddies will be the same. So one of them is a hydrogen. In this drawing to the left, they have an ammonium group. So that is a nitrogen with 3 hydrogens. And it does have a plus sitting next to the nitrogen. So the nitrogen is holding a positive charge, right? So this is sort of one limb. This is another limb. This is the simplest limb. And then we have a carboxylate group, or COO group. So we've got a carbon, it's bonded to another carbon, it's double bonded to an oxygen, and then it's single bonded to a secondary oxygen, which has an overall negative charge. So you do want to know this. This side has a positive charge with the ammonium group. This side on the carboxylate group, we have a negative charge. The positive and the negative neutralize each other. So the overall amino acid sort of carries a neutral charge. Here's the structure 3-dimensionally. There's our alpha carbon. So that is this right here. There's that hydrogen. It's sitting in the back. It's pointing off to the back. Remember, this makes, because there's 4 buddies here, it makes sort of a tetrahedral shape. So there's one of them. Here's the carboxylic group, and here's the ammonium group. And then there's the methyl group, or the R group. Again, this is the thing that changes. Questions on that? Nobody has their camera on today, which is fine, but just let me know if you're having any issues with it. No? Okay, thank you. So we can classify amino acids. There's a few different ways that you can classify them, but one way is to classify them as either nonpolar, hydrophobic, meaning that they aren't going to dissolve in water, or so nonpolar, or polar, which is hydrophilic, meaning that they will dissolve in water. Pretty simply, you can identify them as hydrophobic or hydrophilic, or nonpolar versus polar. Nonpolar means that its side chain, or this accessory that's stuck to it that we can kind of swap out, contains really only carbon and hydrogen. Okay, if it's just a hydrocarbon, carbon and hydrogen, or it looks kind of like balanced, that will be nonpolar. So this is valine. There's that root, right, that we always have. There's our alpha carbon connected to a hydrogen, connected to an ammonium group, connected to the carboxylic group. Same thing here, right? Those are identical. This is what changes. And what we see is here it's just carbons and hydrogens. So this has a nonpolar component to it, or quality to it. Over here, anytime you have a side chain that it itself is polar, or it has ionic components, or it looks really unbalanced, like this is kind of neat and tidy with just carbons and hydrogens. This has like a slosh of different things. This is going to be polar. This is asparagine, or asparagine. I, again, am not expecting you to memorize the names and the shape outside of the lower part of it, right? That is consistent for each. There's a couple different ways that these amino acids can be represented. So with their name, valine, or they can be shortened to a 3-letter abbreviation, VAL, or sometimes they're abbreviated with just a single letter V. Asparagine can be shortened to ASN, or it's got an abbreviation of N for a single letter because A is used on a alanine, I believe. So here are all the nonpolars. Classify them as nonpolar if it's an amino acid that has hydrogen, a simple alkyl, or an aromatic. So if you see a benzene ring in it as well, we're going to go with that is nonpolar. This is really the simplest of them all, glycine, which is your amino acid trunk with just a hydrogen. And we go to alanine, which has got the methyl group. Then we've got an isopropyl group here, right? These are all just carbons and hydrogens. These ones look a little bit more complicated. Here we've got this benzene ring though, so aromatics we classify as nonpolar. Here we do have a sulfur in the center, but because it's sort of lined up in a chain, it has a nonpolar quality. And then this one here, you know, yeah, there is a nitrogen, but overall it's mostly carbon and hydrogen. So we classify this, and this nitrogen is sort of burrowed in this, this ring here, this carbon ring here. So we would classify that as nonpolar as well. This one, this guy here is tryptophan. This is, you find it in a lot of turkey meat. That's why it makes you a little sleepy, helps you to relax. Here are some of the polar ones. Okay, what do you see? If you see an alcohol, a thiol, or an amide, probably going to be polar. So here's an OH, right? Here's an OH. That OH, man, is always very polar because it can make hydrogen bonds with water around it. This SH, it's a thiol group at the end. This thing looks super unbalanced, right? And this looks unbalanced as well. And those are amides. So as far as the structural formulas for an amino acid has an alpha carbon atom that is attached to 3 components. So it's got the ammonium group, the carboxylic group, and then a hydrogen group. The 4th component, or an R group, that's what differs and makes it a particular amino acid. We can abbreviate with a 3-letter or a 1-letter abbreviation. If you're answering questions in your mastering chemistry and it's asking you, what's the 3-letter abbreviation for this? That's not something, again, that I would expect you to have memorized, so just look it up. You'll have like a chart of it in your text. So when drawing an amino acid, all the amino acids have this thing, right? So this is always the base. And usually the way you'll see it written is there's the carbon, the hydrogen will be written on the bottom, the ammonium will be written on the left side, and the carboxylic will be written on the right side. Sometimes it's written grouped like this. Sometimes it's written stretched out where it would be N, H, 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 and they put the plus next to the nitrogen. This would be expanded out to carbon, double bonded to an oxygen, single bonded to another oxygen, and the minus is by the single bonded oxygen. So be comfortable seeing those either way. Every amino acid has a certain pH that it is isotonic in, which means that it's neutral in charge. So this one has a pH of 2.8. So when you see that pH that they're writing out there, that's telling you at what point is the positive charge on the left and the negative charge on the right equal to each other, and you have an overall neutral solution. I'll show you situations where that isn't the case. We can also classify our amino acids, again, as being an amino acid is acidic when the R group is a carboxylic acid. So if at the end you have a C double bonded to an O, single bonded to an O, sort of like what you have going on over here, but it's on the tail end, we would say that that's some sort of acid. a basic amino acid. So we can, classify amino acids as either polar or non-polar, and then we can also classify them as acidic or basic. They'll be basic if they have an amine in them. And when they say amine, it's got like nitrogen with a hydrogen. Okay, so the amine groups here, there's one here, there's one here, and there's one here. We would say all of these things are basic in nature, or remember basic is something that is a proton acceptor. So these are, positive charge, positive charge, positive charge. That means it can take on another hydrogen or another proton. So identify each of the following as polar or non-polar. So looking at this thing, this is really just carbon. It's got 2 hydrogens. So if I was to get rid of this is the simplest amino acid. We put a hydrogen there and a hydrogen there. What is its R group? It's literally just hydrogen. So that's definitely non-polar. This guy here, he's got carbons and hydrogens, but he also has that OH. That OH is what's going to give him a polar quality. So that would be polar. Okay, draw the ionized form for each of the following amino acids and write the 3-letter and 1-letter abbreviations. Again, I'm not going to have you draw these out, but let's look over them. So valine, there is the base that's always the same, right? So you always have that alpha carbon with the hydrogen and ammonium in the carboxylic group. The accessory, the R group, is what changes. In valine, what makes it that is this isopropyl, or it's a carbon with a hydrogen, and it's got 2 limbs coming off of it with methyls. And then cysteine, again, it has that base that's always the same. And what is its defining quality? We've got carbon bonded to 2 hydrogens bonded to a thiol group, an SH group. Here are its symbols. Again, this is all stuff that you're going to be able to just kind of look up. Amino acid stereoisomers. So all the alpha amino acids except for glycine, because glycine is so simple, are chiral, meaning that you can have either an L or a D. So looking at this one right here, here's well, actually, whereas that's an aldehyde. That's not what we want to be looking at. Okay, so here's L-alanine. So there is our, so here's our alpha carbon. There's the hydrogen. There's the ammonium. And there's the carboxylic group. And then there's the accessory. So it's sort of turned on its side. Because this thing has 4 different attachments, it means it can be chiral. And so you can have a setup where this thing is on the left or this thing is on the right. If it's on the left, it's an L. If it's on the right, it's a D, and you classify this. And again, you set it up just like you would your other Fisher projections, where you put the most oxidizing thing on top. So they put the carboxylic group pointing up instead of pointing to the right, where you see it on the previous structures. And you look at what the amino or ammonium group is doing. If the ammonium group happens to be pointing to the left, it's the L. If it's pointing to the right, it's the D. So if we were to look at these and decide, is this an L or a D enantiomer or stereoisomer, it's already drawn for us in the correct way. So they put the Cu on top. Here we've got the ammonium group pointing to the left. Here we have the ammonium group pointing to the right. When it's to the left, it's the L. When it's to the right, it's the D. Again, I wouldn't expect you to draw them, but you might have to identify them, and they'd probably be set up for you in this neat fashion as is. So of the 20 amino acids that are out there, only 11 of them can actually be synthesized in our bodies. So our bodies make protein, right? We are we're not we are machines that make a lot of different things. And one of the things that we produce is protein. But only 11 of those amino acids can actually be produced in the body. There are 9 other amino acids that are classified as essential amino acids. So if you've ever heard of like a supplement and it says, oh, it has all 9 essential amino acids, or, you know, you need to eat, your doctor says you need to eat more protein, you're not getting enough essential amino acids. It's because these 9 proteins our body doesn't produce. It can't make them. So you know, you can't eat one thing and then your body turns it in or converts it into one of these 9 amino acids. The only way your body can get this is it has to obtain it through protein in your diet. So if you're not getting these things, weird stuff can happen to your body if you're not getting enough protein and you don't get these essential amino acids. Your hair can start to get brittle, your skin can start to get dull. You can lose certain amounts of muscle mass, and then there's all like a whole plethora of like neurological stuff that can happen. So definitely want to be getting your protein. And that doesn't mean you have to get it in animal products. You can get it in other ways. So complete proteins, which we would classify really as like eggs, milk, meat, fish, contain all the essential amino acids. So if you're eating a healthy diet of eggs, milk, meat, and fish, you don't really need to be taking supplements for essential amino acids because you're getting them pretty regularly. I mean, these things are flushed with them. Now, if you don't eat those things because of certain dietary restrictions, which again is fine, but then what is going to happen is you're going to have a source of incomplete proteins or incomplete amino acids. So grains, beans, nuts are usually deficient in 1 or more amino acid, which just means you have to eat a variety of them to crisscross so that you've gotten all of your amino acids. You don't want to just eat beans. That would be disastrous for you and for whoever you are snuggling in bed, right? So you want to crisscross them with other things to make sure you've covered all your bases. So an amino acid as either an acid or a base. We talked about, you know, the trunk of your amino acid has this positive ammonium and this negative carboxylate group. When you have when an amino acid with a positive and a negative charge is overall neutral, meaning you've got sort of an equal amount of positive and negative, it says that you are at its isoelectric point. And isoelectric, those 2 things just are balanced. When glycine, so this is the simplest amino acid, here's the consistent trunk, and it's just got a hydrogen stuck off of it. When glycine is at a pi or an isoelectric point of 6, so a pH of 6, that is when this and this are balanced and it has a neutral charge. So when you see that pH, that isn't saying what the pH of the material is, it's saying what is the pH when it will be isoelectric. So the isoelectric point of amino acid is the pH at which the charge groups on the amino acid are balanced and the amino acid itself is neutral. An amino acid can exist as a positive ion if the solution is more acidic or the pH is lower. And it can exist as a negative ion if the pH is more basic or it has a higher pH. And I will show you how that is possible, okay? So, you know, write it down or sort of have this memorized, or you can come along with me and we can conceptually understand why is it positive if it's more acidic, why is it negative if it's more basic? So ionized forms of amino acids. So this is alanine, and this is a simple, this is nice and balanced or charged. It's usually right at around pH of 6, but there's a range of like 5.1 to 6.3 where it is isoelectric. So in this case, Alanine has that methyl group sticking off the top, the bottom in this case. And we've got the ammonium group and the carboxylic group. The positive and the negative here are balanced at this pH. What happens if we take alanine and we put it in a acidic solution? Okay, so I'm gonna add a bunch of acid, or I'm gonna drop the pH. So instead of the pH being at its isoelectric point of 6, it is now gonna have an isoelectric point of something less than 6. Well, what happens is this carboxylic group, see how it has a negative here? It's gonna steal a hydrogen from the acid. It's really, really reactive. And so it's gonna take this and actually turn it into a carboxylic acid group here at the end, and then neutral water. So now we've got a hydrogen stuck to what used to be a negatively charged oxygen. What has happened to the overall charge of the pink side? It now has a charge of 0. But what's going on the left-hand side here on our ammonium group? It's still positive. So what happens to the overall charge? There's no, here we had a positive and a negative. The negative could balance out the positive to give us a neutral charge. Here, we've got a positive, but we have no negative to balance it out. So we just become positive. So now we've got a positively ionized form of this amino acid by dropping it in something acidic, or something more acidic than its PI point. Let's go the other direction. What if we took this thing and we dropped it in a base? Well, if it's in a base, there'll be OHs somehow floating around in solution, whether it's because the metal nonmetal broke apart and gave us OHs, or it was acting as a Bronsted-Lowry and it stole an H from the water. So in this case, the OH isn't really going to play around with that carboxylic side. It's going to mess around over here. This has a negative charge. This has a positive charge with an extra hydrogen. So what it does is this OH is going to gobble up one of those hydrogens, and this will now become H2O. So this OH became H2O by taking one of these hydrogens from the blue side. What are we left with here is a nitrogen attached to 2 hydrogens. Anytime you remove a hydrogen, you take the H off, but you also have to drop the charge down. So now the charge is neutral on this side, but it's still negative on this side. So the overall charge becomes negative. So when you stick it into something that has a higher pH or is more basic than its PI point, you're going to steal hydrogens from one side to give you a negative. Is that clear? On your worksheet, you will have to play around with that. And that is really consistent for any amino acid. So it doesn't really matter what this group is, because we're not changing anything about the R group, right? So we can almost sort of ignore the R group. We're just looking at what's happening at the trunk of the amino acid. Everybody happy with that? Then I'll just keep moving on. Okay. Move forward here. I think we might have a little bit of practice with this too. Okay, awesome, Astrid. So here's sort of a general form, but you'll have your PI point, which is unique to each amino acid. And again, a lot of times they write it under the amino acid. If you become more acidic, that means you're adding more H+. Where is the H+ going to go? You're definitely not going to shove a hydrogen here. This thing's already positive and it's already got 3 hydrogens. This side, though, has an open slot to really pack it on. So you'll stick it here and this positive will win out. If we add OH, we're going to steal a hydrogen. There's no hydrogen to steal from the right side here, or the carboxylic group. You have to steal the hydrogen from the ammonium group. So you get H2 with the N, we're down a hydrogen, we're down the positive charge. This positive should be sitting over here, not above here, it should be right here. Let's just go ahead and get rid of that. for later notes if people are watching this video. So we want the positive right about there. We lose the positive, but we keep the negative, so we get a negative ion. So high pH negative, low pH positive. All right, so looking at these two, which structure represents alanine at a pH above its pi and alanine at a pH below its pi? So I'll give you just a minute to identify that. Okay, so you want to find the alpha carbon, and then sort of, I like to circle out what is important, which is the base, the root, or the trunk, right? We don't really need to worry about the accessory group. So here, what I can see is I've got a positive charge here and I've got no charge here. So this thing has an overall positive charge. Where do we get positive charged ions? Positive is going to happen when we are acidic. You either memorize that or you think, an acidic solution has got a bunch of hydrogen in it and there's an extra hydrogen that's throwing off the charges. This guy over here, what's going on with my charge? I've got a negative charge here and I've got a neutral charge here, which gives me an overall negative charge. That means we are down a hydrogen. If I'm down a hydrogen, that is a basic solution. Doesn't change with the R group shifting. So here we've got another thing that says what? Consider the amino acid leucine with a pi of 6. At pH of 3, how does leucine change? Okay, so if the pi is 6, if we go to a pH of 3, that is an acidic solution. It means we're going to have excess H+, lots of H+. Okay? Or lots of H+. That's going to, I'll give it a little arrow to say we're increasing it. So if I've got hydrogen to smush on here, where am I going to smush the hydrogen? Not going to put it over here. I'm going to stick it right there where that negative charge is. That negative charge, oh, it just wants to gobble up the hydrogen. So if we gobble up the hydrogen here, what do I have? I have a positive charge. How does leucine change? It becomes a positive ion. What if we look at the second scenario here where we have a pH of 9? That's basic. We're going to get rid of H+. Okay, it's going to decrease. Where can we steal an H+ from? I can't take it from this side. We don't take it from here. I'm going to take it from here. So this is going to go down to a 2 and the charge is going to disappear on that side. So we have only a negative charge. So this will be a negative ion. Questions on that? Again, doesn't matter what the accessory is here. We're looking at the root. Okay. So we're going to start talking about proteins now. We initially were talking about amino acids. Those are like the building blocks of proteins. So just like, I've used this analogy before, but you have letters that make words and words that then make sentences and then stories, right? So the amino acids are like the letters. So we're going to put the letters together into a chain, and that is classified as a primary structure, a primary protein structure. Primary because it's the first kind of connective quality of a protein. We'll have secondary and tertiary and quaternary. So how do we stick these amino acids together? We do it with what's called a peptide bond. I don't know if you guys have heard the word peptide. They put it in like a lot of skincare, peptides. They put it in a lot of fitness milkshakes and stuff like that. Oh, it contains peptide bonds. And what is a peptide and peptide bond? It's how you attach to amino acids. If in this structure here, so I've got, and we'll go over this in more detail, but here's my alpha carbon, okay, on one. So I'm gonna just circle the alpha carbon, and here's my alpha carbon on another one. Here's the carboxylic group of one, and here's the amide group of another. So we bond the carboxylic to the amide of the other. And that will be classified as the peptide bond. And we will go further into that in a minute. So the linking of two or more amino acids by a peptide bond forms a peptide. If it's two, it's called a dipeptide. If it's three, it's called a tripeptide. If it's four, it's called a tetrapeptide. Proteins are much longer than 2, 3, or 4. So anytime you have, a long chain, we call it a polypeptide. And so to form a peptide, we have to have this peptide bond, and a peptide bond is an amide bond. Amide being that there's a nitrogen, hydrogen in it. So I have glycine over here, and I have alanine over here. And I'm gonna just box off the R group so that we can just sort of like visually like ignore it. Okay, so why don't we then fill it in? Because this peptide bond is not happening off the R groups. It's happening off that trunk. So here's the carboxylic side, or the pink side of this thing. And here's the ammonium of this side. A lot of times they call, this like the end terminal. So that's the starting side, and then the C terminal is the carbon side when we've connected them together. All right, so in order to bond these things together, I want to get the carbon bonded to the nitrogen. So I've got to get these things out of the way. So the oxygen needs to go bye-bye. This hydrogen, and not just this hydrogen, but actually a second hydrogen. So this hydrogen and this hydrogen need to go away. And we're going to bond the carbon directly to the nitrogen in a single bond. Now we've gotten rid of an oxygen and 2 hydrogens. What's oxygen and 2 hydrogens? That's just water. Okay, so water does get released when we're making one of these polypeptide chains. And this thing right here becomes our peptide bond. And it's now stitched to amino acids together. Nitrogen can at times be happy with just 3 bonds. So I know that might seem a little weird. The carbon still needs its 4. It's got 1, 2, 3, 4 double bonded with the oxygen. The nitrogen, though, we've dropped off one of those. That is always how these things are going to stitch together when it's a peptide bond. We take these off, and then we stick these 2 things together. You'll see that the nitrogen loses that positive charge as well. So we don't have that positive charge. But we still have, this is a dipeptide. We still have a positive over here, and we still have a negative over here. The positive side where the amine is, we call this the N terminal end because it's got an N. This we call the C terminal end because it has the carboxylic or the carbon group. And because these are open, right, this could get attached to another amino acid, right? And this could get attached to another amino acid. And so you always have like these sort of open slots at the end that could just propagate the chain. So formation of a dipeptide. This is in 3-dimensional space, but there is the carbon from the carboxylic. Here is the nitrogen from the amide side. We are going to take the single oxygen, the single bonded oxygen, and 2 of the hydrogens off. That will be the water. And then we're going to stick the carbon directly to the nitrogen. And that's what's happening here. There's the carbon directly bonded to the nitrogen. The nitrogen now only has 1 hydrogen. This is still double bonded to that oxygen here. And that we classify as our peptide bond. When we start chaining these things together, we've got to name them, right? So a lot of times they're named using their abbreviation, either the 3-letter or the 2-letter. You can smush the names together though too. So if this is glycine and alanine, they'll call it glycoalanine. So they take the IN off of the first one and they just sort of smoosh it together. Or you'll see it written as gly-ala. It's 3-letter abbreviation, or GA. If you've ever seen like those really complicated helixes of DNA, and it's got the G and the A and the T and the C, I believe. Those are all just amino acids that are strung together. Okay, so we want to draw the dipeptide. So I want you to draw the dipeptide here. We've got serine and I don't know what the THR is. Biochem is not my strongest place. So help you out. This is the alpha carbon here, and this is the alpha carbon here. I want you to smoosh these 2 things together. Okay, so we're going to smoosh this and this together. Go ahead and you do that. And I'll give you all 2 minutes for it. All right, so the setup here is the same as what we did before. Yeah, we've got, you know, a bunch of junk on the end, but we can just add that in after the fact because we're really just looking at this. So I've got my carbon bonded to my hydrogen. This isn't going to change at all, so I'm just going to write that in. So we've got NH3+. What is going to change is what's going on here, right? So we're going to ditch this and 2 of those hydrogens. So this will be bonded to a carbon, double bonded to an oxygen, but now this carbon is going to be single bonded to the nitrogen, right? The nitrogen is only going to have 1 hydrogen. It's going to be bonded to its alpha carbon, and it's going to have that carboxylic group at the end that hasn't changed, so still negative. What happened to the oxygen and the hydrogen? It became water, so let's just add that to the end. so that we don't just have water disappearing. And then we want to add the accessory, right? So the carbon with the H2 and the OH group. And then over here on this alpha carbon, I'm going to add the carbon that has the offshoot of the alcohol and then another carbon methyl. Okay, so that ends up being the structure. Where is the peptide bond? Again, the peptide bond is happening right there. Let's look at their drawing because it's probably a little clearer than mine. There we go. Yeah, so our peptide bond right here, that is what's stitching it together. Questions on that? A peptide bond doesn't change. Doesn't matter what two things you're mixing together, how many of them you're mixing together, it's just sort of a repeat of that over and over. Okay, so as far as naming peptides, with the exception of the C terminal, so we always write it where the nitrogen one is sticking to the left or the start, and then you read it like a book, and the C is pointing at the very end. So with the exception of the C terminal amino acid, the names of all the other amino acids in the peptide will get a YL. So this is alanine goes to alanyl, glycine goes to glycyl, serine will stay serine. So this is anylyl glycyl serine. So YL, just like when you had the methyl group when it was an accessory. You also can do it with the shortened alaglycer or AGS. So this says write the 3-letter abbreviation in the name for the following tetrapeptide. You're gonna be able to look this stuff up because I don't expect you to have all these memorized and their abbreviations. So we have alanine, leucine, cysteine, and methionine. The first 3 here will get a YL. The last one we keep the same. So we've got alanyl, leucyl, cysteanyl, methionine, or the abbreviation of al-leu-cyst-met. That's a mouthful, isn't it? So back to this idea of the primary structure of proteins. A protein, again, these really large polypeptide chains of at least 50 or more amino acids that will produce some sort of biological activity. The primary structure of a protein is the particular sequence of the amino acids that are held together by polypeptides. So we first have our primary structure, which is kind of like putting the letters together in a word in a specific order. That would be a primary structure. Peptide bonds, stitching them together. Okay, so thyroid hormone that stimulates the release of thyroxine is a tripeptide with the amino acid sequence GLU, HIS, PRO. Although other amino acid sequences of these 3 amino acids are possible, only this specific sequence will produce the correct hormonal activity. So it needs to be GLU first, then HIS, then PRO. That is the magic combination for this thyroid hormone. Primary structure of insulin. Okay, so insulin was the first protein to have its primary structure determined. So there was a point in science where they didn't know these things about proteins. They didn't know the sequences. They didn't know the amino acids. And one of the first things that they were able to chart or lay out sequentially was insulin. And so this is insulin. There's an A chain and there's a B chain. So there's 2 primary chains and they're bonded together by this sulfur bond. So it has a primary structure of 2 polypeptide chains linked by the disulfide bond. It has chain A, which is 21 amino acids, and chain B, which is 30 amino acids. And it's always this, like it doesn't change. Like it needs to be in this ordering in order for it to be effective. If you start changing these things, it will either lose efficiency or it will just not work at all. Okay, answer the question for this tripeptide that is shown below. So here's our tripeptide. Here's our N-terminal. Here's our C-terminal. What is the N-terminal amino acid? I don't even know. I don't even have that memorized. Okay, what is the C-terminal amino acid? Where is that guy over here? This is what, alanine. What is the name of this thing? So you would, again, just look up what these accessories are and label them from there. Phenylalanine, phenylalanyl cystenyl alanine. Ugh. All right, write the names and 3-letter abbreviations of the tripeptides that could form from 2 glycines and 1 alanine. I do want you to try this, okay? So we have glycine, 2 glycines, and 1 alanine. There's a bunch of different ways that those can be combined. So go ahead and do that. Well, there's really only 3 ways that it can be combined. So try and mix those up. I'll give you a minute. And the abbreviation for this is GLY and ALA. So try and mix and match those. Okay, so if we have 2 glycines and 1 alanine, the possible combinations, we can have a glycine, starting with a glycine and an alanine. We can have a glycine and put the alanine in the middle and the glycine at the end. And we can have an alanine, a glycine, and a glycine. These 2 things are not the same, this one and this one. Some people may say, well, can't you just flip this around? Well, there is a specific ordering and as far as what's open, right? So on this side, this glycine has its amine side open, and this alanine has its carbon, right? This is our N terminal. This is our C terminal. On this one, the alanine is the one that has the N terminal. The glycine is the one that has the C terminal. So those are not the same. Here, glycine has got the N terminal. Here, glycine has the C terminal. So those will have different effects or properties. So proteins, I mean, insulin is two really long chains, but even that's kind of more complicated where those 2 chains are bonded together. So when we're talking about proteins, it's not just the primary structure, right? We're not just making words. We have to thread those words together, have them interact with each other. So proteins will also have these things called secondary, tertiary, and quaternary structures. And they build up on top of each other. So first you have your peptide bonds that makes a single chain. Then we can add a secondary structure. Then it can be compacted into a tertiary structure and a quaternary structure. This staircase, which kind of looks like DNA, right? That has this alpha helix, and alpha helix is an example of a secondary structure. So here's the alpha helix. In a secondary structure, for this one, hydrogen bonds form between the carbon double oxygen bond group and the amine group of another amino acid, and they'll sort of stick together. So instead of this chain just being like one long limp chain, it starts to curl in on itself because, you know, the carbon oxygen on this chain sticks to the hydrogen nitrogen on this chain and it pulls it together. And it's good that it does that, and that, you know, specifically like our DNA does that, because this is a very efficient way to store information. If it was just a single long chain, if we uncoiled our DNA, I don't know, I feel like I read somewhere that like it would stretch out to the moon and back or something. And so in order for it to fit into our bodies, it needs to fit in there efficiently. So the formation of a bunch of hydrogen bonds along with polypeptide chains give the helix shape, the staircase. So we've got this hydrogen bond pulling it together. There's another type of secondary structure. Not all protein forms that pretty double helix. Sometimes it can form what's known as a beta pleated sheet. In this secondary structure, we've got these chains. So here's one chain, here's another chain, and the chains are attracted to each other through a hydrogen bond. But it will form, so it forms the sheet, right? So instead of it being a single chain, it's these chains that are linked together. And then the chains themselves through hydrogen bonding will bend or pleat. Like if you've ever made one of those paper fans where you fold the paper back and forth, that's what you get. And you'll get this nice polypeptide sheet. And again, this is much more efficient than just having one long chain. There will be a carbon terminal and there will be an N terminal, nitrogen terminal. Another secondary structure that we have is a triple helix. So it's kind of like the alpha helix, except it's 3 chains that are helixing together. We have hydrogen bonds that will hold the chains together, giving the polypeptide additional strength. This is what your collagen and your skin is made out of: connective tissue, skins, tendons, cartilage. This structure, with time, as we get older, we're just not as effective. Our bodies aren't as effective at like turning over cells. This interlocking triple helix will start to weaken and stretch out, and you might lose strength in your connective tissue, in your skin, your cartilage, and your collagen. So you can kind of think of this as, again, we're like building up on the hierarchy. So we have our primary structure, which is just the amino acids chained together with a polypeptide bond. We have a secondary structure, which can be an alpha helix, a beta pleated sheet, or a secondary structure like a triple helix. Again, these secondary structures are a lot of times happening between hydrogen bonding, and they create like a more compact chain. Now we can take these secondary structures and we can create what's known as a tertiary structure. In a tertiary structure, and you will want to know these things, like it's determined by the crosslinks, you will want that. It's an overall 3-dimensional shape caused by the interaction of different parts of the chain, causing it to bend and twist. So I know in the alpha helix, it seems like that's what's happening. And in the alpha helix, you do have interaction, but it's happening between things within the same chain. So here, right, we've got this single chain, and it's interacting with itself, but with hydrogen bonding. Now what's going to happen, we can kind of think of this as like a phone cord, right? It's coiled because it's more efficient, like an old school phone cord. Now what's going to happen is this curled up structure is going to start to interact with itself. So it's determined by crosslinks, which is the attraction and repulsion between the side chains. And by the side chains, I mean those R groups, so those accessories of the amino acids. So when looking at this structure, I've got this alpha helix that's curled up, right? So this is the phone cord curled up. That phone cord that's curled up will now start to interact with other parts of the phone cord. So if you've ever had one of these old school phone cords and they start to like bend and compact, that is sort of how our tertiary structure is going. So we've got, the single or the primary structure, which is just stringing it together, the secondary structure, which is curling it, and then the tertiary structure is folding that curled chain. We can get all sorts of different tertiary structures. We can have bending of that, alpha helix or triple helix or beta pleat because of hydrophobic interactions, which is between two nonpolar amino acids. So if they're both nonpolar, they can have an interaction, hydrophilic interactions between the external aqueous environment and an R group that happens to be polar. You can have these things called salt bridges, which are ionic bonds between two parts of the chain. So again, when you're looking at these amino acids, right, they have these accessories popped off of them that have all sorts of different junk on them. And that junk is going to interact with other junk in the chain. Hydrogen bonding is also something that we see in tertiary structures. So we will see hydrogen bonding with R groups. And then these disulfide bonds, where a sulfur and a sulfur bond. This is what happened, or what you saw in that insulin picture. So where are you? So here we've got, you know, a chain, and a chain that's a primary structure. I'm not sure if these are curled. That would be, you know, my guess, or if they're pleated for a secondary structure. But this right here, this sulfur-sulfur bridge, is a tertiary structure. Here's, what is this? Oh, on sickle cell. So sickle cell anemia is caused by an abnormality in the shape of one of the subunits of your hemoglobin protein. So here is a normal genetic chain for hemoglobin, and we'll have this glue here, which is a polar amino acid. Now, if you have sickle cell in that same chain, where there should be a polar amino acid, you actually have a non-polar amino acid, valine. So the 6th amino acid, which should be polar, is now non-polar. Doesn't seem like a big deal, right? Everything else is the same. Well, the problem is that the non-polar R group on the valine here is attached to the non-polar regions in other areas. So this will actually sort of stick to other parts of the chain, whereas this thing wouldn't stick. And so the chain starts to stick to itself in a way that it's not supposed to, which causes the red blood cells to actually sort of curl in on themselves and form this kind of rounded shape. So here we have what would be classified as a standard red blood cell, where the chain doesn't have that sticking. Here are what a pretty severe sickle cell is, where that nonpolar group is starting to curl in on other parts of the protein chain. The red blood cells that move through our body move through very small places, and they move very quickly, and they move continuously all the time. So this round shape is the most efficient thing for them, because they can sort of boom, like bounce into each other, right? Like little jelly balls, and continue on their way. If you have something that has a sickle or a hook shape like this, and here's the beginning of a red blood sickle cell, these things can actually catch on each other. Whereas these things aren't going to catch because they're a sphere shape. This can hook onto another sickled cell, or even onto a healthy blood cell. And it can cause clogging in your vessels, in your capillaries. It can cause inflammation and a lot of pain. It can decrease the amount of oxygen that you get to your tissues, because these things can't move really efficiently through your body. And then probably the scariest thing is it can cause strokes, right? Clots and strokes, blood clots and strokes. So it is very, there's a very important reason that these are sequenced the way that they are, not necessarily that, somebody said, oh, I'm going to sequence them like this, or some entity did that, but just the fact that, evolutionarily speaking, that these were put into an order that was most efficient. This one here with sickle cell is just less efficient, unfortunately. Okay, so indicate the type of protein structure as either being primary, beta pleat sheeted, an alpha helix, or a triple helix. So I'll have you do those. Give you a minute. No, I won't. It's 9:12. Okay. I got carried away. So we will finish up this chapter on Wednesday. You will have your test 5 on Sunday, Monday, and you will have your final accessible on Monday, Tuesday only till 5 p.m. If you have any general questions, just throw them out. If you have any personal questions,